Welcome everyone to this course. So, now since we have written the summations of Wi's with respect to W and epsilon m, right. So, this will become capital W times e power minus alpha into 1 minus epsilon m plus e power alpha times epsilon m. Okay. What we need, this is L. So, now we will have to find an alpha star such that this L is minimized with respect to alpha. Therefore, consider the derivative of this with respect to alpha and put it to 0. If you do the algebra, I will skip it. So, you will get alpha star to be equal to half log 1 minus epsilon m divided by epsilon m. Is exactly what Adaboost says, no? Please do this, right. I mean, just simply skip the algebra, just do that. I mean, just rearrange, take the derivative and rearrange the terms and you will get it. So, that is it. So, we completed the Adaboost algorithm. So, now what did we say? Let me just run through the algorithm again. So, start initialize uniformly, right, and then you get the current classifier that would minimize the weighted sum of misclassified samples, define this epsilon m and estimate the optimal algorithmic step as alpha m and update the new weights using this equation. That is it. This is nothing but gradient boosting, okay, with exponential loss function, okay, and optimizing over the alphas as well. Okay, that is why gradient boosting is a very generalized way of looking at things. So, Adaboost is, in fact, Adaboost is one of the most powerful algorithms that are out there. So, you can, even today, a lot of the industry grade classifiers use Adaboost, because we saw that ensembles always decrease the variance, right, if, in turn decreasing the error. So, you have multiple, it is very cheap to learn weak learners. You do not have to do a lot of hyperparameter tuning also, you just have to ensure that your learners are better than chance and then boost it using this. It is very easy to run a boosting algorithm. In fact, you can see, I will give that as an assignment. So, now there is, if there is a data set on which you are solving a classification task or a regression task, now take one learner and try to do an optimization by hyperparameter tuning and parameter tuning, you get some number, right. Instead of that, use some hundreds of learners, all of them are weak learners, you do not have to do any hyperparameter tuning. Chances are that this ensemble will beat the optimized individual learner. Okay. Right. So, this is about boosting. Since we are talking about bagging and boosting, I will also talk about an evaluation technique that is often used in literature, which is called cross validation. What happens in practice is, let us say that you are given some data set like this, right. So, which has n samples here. So, typically what do? We split this as train, validation and test, correct, and we train our algorithm on training data set. In fact, this is not to scale, let me just change it the way it is done. So, typically this is how it is done. If you have 100 as your training data, right, you split it as 70 20 10, okay, or 60 30 10 or 60 20 20. The training data always is much larger, orders of magnitude larger than the validation and test data. So, that is how you do it. So, this is find the parameters of the algorithms from here. So, you get the hyperparameters from here. And report accuracy or report metrics on this. And we have seen that while you are building an algorithm, you never look at the test data, right? All the tuning, all the parameters and hyperparameters are tuned on the test, the training data and the validation data. Okay, you never look at the test data. See, now here what happens is this induces a bias in terms of even within a data set. Okay, you are fixing the subset of the data set that's always taken as training data. Okay, now which is again bias. Right? You are ultimately when you report the final metric, performance metric, you are reporting only on some 10% or 20% of data, and you don't know how the algorithm performs on the other subset of data. That is why typically what is done is you take this technique called cross validation, okay, where you rotate between the training test and validation split. What does that mean? Let us say that we are doing this is called k-fold cross validation in the literature. It is a 5-fold, 10-fold cross validation and so on. If it is a 5-fold cross validation, what you do is that you do 5 non-overlapping 80-20 splits of data, or 70-30, 70-10-10 splits of data. These are all non-overlapping in the sense that 10% of test data that you look at is different for every split. Okay. Now you build your algorithm on those 5 different data sets. So this is actually sampling with replacement only, but you are doing not randomly, you sample with replacement with a specified pre-specified procedure, that's it. Okay. Now you have 5 classifiers, or rather 5 performance metrics on 5 different data sets, 5 different test data sets. Report the final number as an aggregate over all those 5 data sets, 5 test data sets. This is called cross validated numbers. So typically when people, if you want to evaluate your algorithm for robustness, the best practice is to report the cross validated numbers, not do one random split of data. So what are you doing like this? By doing this, you are ensuring that you are testing the performance of the algorithm on entire data set, because if you are doing 5-fold cross validation, then you are splitting data into 5 different non-overlapping sets, right. So you will have every 20% of the data being treated as test data in one fold. Okay. So that way you aggregate the performance, or rather you will report the performance across the entire test data set is the idea. So this is called cross validation. It is a good practice to report your metrics after cross validation. Yeah. Yeah, you have to train. See, this is independent of ensembling. If you are doing an ensemble, you will have to do an ensemble on each fold separately.
So this will validate our choice of models, but what models we actually exported?
I didn't get the question. What's the question?
Because we are reporting average accuracy of different data sets for different models. Finally, what model do we export?
So the question is, when you cross validate, you will get, let's say, k number of classifiers. What should be your final classifier? Either you can do an ensemble on them. That's one way to do it. Okay, you back them and do it, or you get ship the one that is the best amongst these 5. Okay, and anyway in the field you don't know how your classifier performs, right, on the unseen data. So you have to ship one. You can ship any one of them, or the ensemble of them as well. Okay. Okay, so
normally test data is considered as unseen data, right? But in this method, test data which we are considering is already exposed to the model.
not when the model is being trained. Not when the model is being trained. When one particular model is being trained, it is not seeing the test data at all. No, this is like training 5 different or k different classifiers on k different data sets, which are sampled from one large bag of data sets that you are given. You understand? Even now, every individual classifier is not being exposed to the test part of it. Yeah.
But if we export the ensemble, the whole thing has been exposed to.
That's okay, but that's why I told you. Finally, when you ship, right, the test data that is being fed to the final classifier is anyway unseen to this, isn't it? So, this is, as I said, typically cross validation is used to measure the robustness of a class of algorithms across different splits of data. So, when people ask you to report the metrics, they will not ask you to report. See, what happens is, suppose I give a particular classification problem on a data set to 2 people, and I ask you to report the performance on a 70-30 split. What is that 70% that you choose and what is the 70% that the other person chooses is very different. If I ask you to cross validate, then I can compare the performances much better is the idea, isn't it? Because no matter what split do you take, if you do a 5-fold cross validation and if the other person also does a 5-fold cross validation, then both of you have seen like all the parts of data, that is the point, or rather the algorithms have been evaluated on all parts of data. Okay. Yeah.
If you are splitting the data set into 5-fold or 6-fold small subsets, then each classifier is getting a small number of points. Won't that reduce the accuracy?
Why is that? Not necessarily, right? See, if you are doing a 70-30 split or 80-20 split, I am saying every classifier now will get 80% of the data as training data, no? The only thing is which 80% of the training data a classifier would see changes across different folds.
But each individual classifier is getting like less number of data points.
Why? Everything gets the exact same number of data points, right? Because there are 5 different 80-20 splits.
I'm telling like instead of training on a very large data set, we are splitting.
See, anyway you are splitting it for test data. I mean, you are not training on 100% of data anyway, right? You are doing it on 80% of data. What 80% gets deferred, that's it. Okay. Okay, so that's about it. I mean, that's all I wanted to talk about in the realm of supervised learning. Okay. Now let's go to the next paradigm in machine learning, which is called unsupervised learning. We will stop here and continue in the next lecture.